Now it is the second part of section 7.3, Fisher's LDA, the optimal projection. In this part, we'll try to solve the optimization problem of Fisher's LDA. We first rewrite the Fisher's objective function, here JW. Here mu k is the mean of point in class K, and mu k tilde is its projection. Now sk tilde squared is the within class scatter. Okay, here we define matrices that is defined because of this derivation. Now for this denominator, for each term, sk tilde squared is defined in this way. Now using w and x, we can rewrite in this way. Basically this is a dot product, so that here we reach at that, and then now w transpose and w can be now out of the summation because it's independent of the summation. So we reach at this expression. Now we define this term as sk. Here we defined it, and now the numerator has two parts, so that we are adding the s1 tilde squared plus s2 tilde squared. That can be this one, and sw is defined to be s1 plus s2. So this one is for the denominator. And here s tilde w is the within class scatter, and sw itself is the within class scatter metric. Okay, and similarly, we can do the same derivation for the numerator here. mu1 tilde minus mu2 tilde squared we have here, and there's again in the product, so that dot product, so that we can reach this expression. And we define this portion as SB when we have that. Now SB tilde is called the between class scatter, and SB itself is now between class scatter metric. Okay, now here we have one remark. Because SB is made with auto product of two vectors, so that the rank of SB must be less than or equal to 1. If it is non-zero, then rank is 1. Okay. Now, by using the metric or vector we defined, we can rewrite the Fisher's objective function in this way. Now here, we have to solve the problem. Applying some algebra, we can reach at and in this way. And so it becomes now generalized the eigenvalue problem. Here, SW inverse and SB, now W is now same as JW times W. Here in algebra, we assume that norm of W is 1, and then you can easily reach at here. So we have to solve the problem. So eventually, W, the projection vector, is eigenvector the metric. And if you write down this one in this way, then it is generalized the eigenvalue problem. And also we can see that here, and SB is rank 1, so that this whole thing is a rank 1 metric. So there's only one non-zero eigenvalue. So here, JW will be the non-zero eigenvalue. That means that if you try to maximize this quotient, then now the maximum value will be the non-zero eigenvalue of this metric. Okay. Okay. So here we summarize. Finding the eigenvector of SW inverse and SB associated with the largest eigenvalue is this problem. So here, now W is the vector such that it will make this quotient maximized, right? Okay. So this one is known as the Fisher's LDA, and so we have here now small experiment. Okay, now these two and two classes, and we try to find the projection vector for these synthetic data points, x1 and x2. So here now, these are x1 red points, and that is x2 in two-dimensional space. For this two-class problem, we try to find the projection vector W star. Okay, we follow exactly the definition mu1, mu2, the mean of x1 and x2, and then now we define S1 and S2, and within class scatter metric is defined in this range. So after, okay, that is output from these data points, and I try to put here now output. After computing this one, I try to see print out the output, and I put here. Okay, now this one is a between class scatter metric, and output is given in this range. Now, inverse of SW times SB, for that one, we try to find the eigenvalues and eigenvectors. Your V1 is that one, and V2, and here we have the non-zero eigenvalue, that is here 1.0476, and the other eigenvalue must be 0, because it's rank 1 metric. The one eigenvalue must be 0. Okay, so here V1 is corresponding to the non-zero eigenvalue, so that is projection vector. Now, here we have the projection vector here, and that is V2. So we'll not project this direction, we'll do that direction. So here, these points are projected point from the class 1 points, and these are projected point from class 2 points. As you can see here, the projected points are well separated. Okay. Okay, that's the end of part 2. Thank you.